מקליט, יאללה. אתה יכול להתחיל להעביר את הפרזנטציה.
בסדר, וכמובן זה לא יהיה פרזנטציה כזה.
לא,
כן.
אני נותן את זה לשכתוב.
כן, חכה שנייה, כן, אני מנסה לעשות פול סקרין, כן, אני עושה פול סקרין, אתה רואה פול סקרין,
כן.
כן, טוב, אז אני, תכף, זה לא זז לי משהו.
מעולה.
תכף אני מנסה קוויק לעשות מזה. לא. זה פשוט, אתה רואה, יש לי משהו קטנצ'יק שם, בצד, למטה, כן?
כן.
אבל זה, כן, אני לא יכול להזיז את זה.
תלחץ על הסימן הזה, הכחול, לא?
לא כחול.
כן.
בסדר, זה לא מפריע כבר.
לא.
בסדר. תכף. רק משום מה הם זזים נורא לאט, עכשיו אני לוחץ בשביל להעביר את זה. לא הבנתי. זה כנראה בגלל
זה שזה מצלם.
יכול להיות, אבל הוא לא מגיב. המסך לא מגיב לי. לא יכול לצאת מזה. לא מבין.
תלחץ כאילו יכול להיות שאתה עכשיו בתוך זה, תלחץ על הפרזנטציה עצמה. כן, ותנסה עכשיו להגיב.
כן.
כן, היית פשוט במסך. אז רגע, אני עושה.
מפריע לנו זה הקטנצ'יק הזה, כן? כי אני לא יכול להעלים אותו.
בסדר.
כי אני שם אותו פה. כן, בסדר.
מתחילים.
טוב, מתחילים. So we will talk today about a new paradigm, new vision on the seismic data processing and imaging, which is based essentially on the idea of multifocusing. To begin, I will start from quite general few statements. אני מנסה להעביר, אבל הוא לא עובר.
תלחץ פה. יש לך על החץ הזה למטה.
כן. So first I show you two images. One is from the conventional imaging procedures and another from the new multifocusing procedure. And it doesn't matter which kind of imaging it was, just stack or time or depth migration. So when we compare these two images, it's clear that the new multifocusing imaging is much superior than the conventional. And the question which we can ask naturally is how this can be done, which tools, which magic we use to get such different such advantages of the new technology. To answer this question, we start from the general ideas of seismic imaging. Undoubtedly, ופה אפשר, מה שכתוב זה מאוד יפה. Undoubtedly, the depth imaging without reservations is the aim of seismic exploration method, and to have a depth imaging successful, the knowledge of velocity model is crucial. So the main point of all the data processing and analysis is to extract information for building of velocity model. This can be done at least in two ways. One way to achieve the velocity model, to build the velocity model, is to work directly in the depth domain. And this is the most popular and usual or common way to build the velocity model today. We work directly in the depth domain, trying to updating the velocity model using different criteria of depth migrated gathers. An alternative approach is to extract requested parameters of velocity model information directly from the original data. which means to work in time domain and to try to extract the most information we can. So these two approaches are not in competition, but rather they complement each other. So what I'm going to talk today is connected to the second direction. It means to work directly in time domain using the original observed seismic data to extract as much information as possible and to, according to this information, to build and to update the velocity model before we go to the depth imaging. So I will build my presentation on the scheme. אני לא בטוח שזה משהו שאני דיברתי, אבל...
לא משנה.
אוקיי. כן, כן, כן. So, what is here? So the first step of or the basic, the fundamental step of our approach is Prestack data analysis. The main information about the propagating media is contained in the waves propagating in this media. And the information about these waves we need to build the velocity model, we can extract from the wavefront parameters. So the information about the wavefront parameters are crucial for successful building of a velocity model. So in fact, this is the first and fundamental step of multifocusing. When analyzing the observed wave field, we estimate the wavefront parameters. And this is based on so-called time fields. So the time information, the travel time curves, travel time surfaces of the observed reflected and other kinds of seismic waves. So here we see some very simple model, which is shown in depth and midpoint and offset axis, and the travel time surfaces, which in blue we see the actual travel time surface, and in green we see the travel time surface or part of the travel time surface, which approximates the blue surface around the imaging point P. The purple line shows the traditional CMP, common midpoint trajectory for this point. So if we knew the green surface, we could efficiently stack the data along this surface, around the point P, and have a very good imaging of the point P, of the imaging point. So this is, in fact, this is the basic idea of multifocusing, is to find from the data, to find the surface, the green surface, which approximates the actual travel time surface, and to estimate the parameters of this surface. These parameters is, this surface is approximated by second order curve, which multifocusing gives an explicit representation of this surface, and the surface schematically can be approximated by some function, double square root function, which is written here as f, which depends on geometry, source receiver distances from the imaging point, and number of unknown parameters. For 2D, for two-dimensional case, we need to know, or we need to estimate from the data three unknown parameters, which are signed here as beta, the normal incident angle, emergence angle of the normal ray, and two radius of curvature, of two fundamental waves of the ray theory, RCRE and RCE. Besides, we have to know or we assume that we know the near surface velocity V0. So these two radius of curvature, they are so-called normal incident point wave, RCRE, and normal wave radius of curvature, exploding reflector model, RCEE. And the beta, as I said, it is emergence angle for the normal ray. In 3D case, the situation is much more complicated, and we have, instead of circular approximation for the wavefronts, we have a 3D approximation, and the number of parameters increases from 3 to 8. So we have two angles in x and y directions, beta x and beta y, and 6 radius of curvatures, 3 for each fundamental wave, 3 for RCRE along x direction, radius of curvature along the x direction, along the y direction, and the mixed derivative, radius x, y, for the normal incident point, and for the normal wave, 3 parameters. So in totally we have 8 parameters. So if we knew these 8 parameters, we could accurately approximate the wavefront around any arbitrary point. So the main purpose of the multifocusing Prestack data analysis is to estimate these parameters from the observed data. Okay, this is not important. This is I show just these parameters. Now I'll say a few words, because this is just a technology. How do we estimate these parameters? We do it, this estimation, we do this estimation similar to the procedure. We do estimation of stacking velocity in the conventional processing. We analyze the data, so we scan for each particular time sample, and for each arbitrary CMP location. We search, we scan all possible combinations of the parameters, of the wavefront parameters, and we compute some coherency measure which characterizes the signal-to-noise ratio. For example, semblance. Yeah. Scanning all possible sets of parameters, 3 in 2D case and 8 in 3D case, we find the combinations which provides the maximum value of the semblance. These sets of parameters are the parameters which characterize the wavefront. Okay, based on these parameters, now we build all our processing and imaging flow. Yeah? So I will show you only principal procedures which we use for data processing and imaging. And the first thing we can do is to enhance signal-to-noise ratio in the Prestack gathers. So Prestack signal enhancement. Instead of estimating the global parameters, instead of approximating the wavefront global way for all the offset, we can estimate these wavefront parameters locally around each position for each time sample and for each offset. In this way, we can overcome hyperbolic approximation for travel time approximation, and it's shown here. If we assume that we estimate the wavefront parameters around point A for particular offset, yeah, and we don't estimate the green surface, we approximate only the brown surface, local approximation. Then this approximation, which is as well second order approximation, can change from offset to offset. In this way, there is no more the hyperbolic approximation for the total time surface. As a result, the local stacking, local stack around point A, according to the estimated parameters, increases the signal-to-noise ratio. The examples are shown here, so the original gather and the same gather after press-stack signal enhancement, and you see the essential increase in signal-to-noise ratio when we preserve non-hyperbolic character of the arrival travel times. Several other examples: original data, the data after enhancement, and so on. I have to say that one important point, that multifocusing technology works from the surface, and taking into account the topography. And you can see on this example, yeah, when the data is length data from very sharp topography, you see all this non-hyperbolicity mostly connected to the topography. Okay, another application I show you is static correction. So this is especially important for land data, and especially in difficult areas such as foothills. The multifocusing static correction solution is based on the surface consistent concept, which is used in conventional processing, but we use the multifocusing press-stack signal enhanced gathers to estimate the time shifts and to estimate the necessary pilot traces in the static solution. As a result, you see in this example, this is the stack with standard static solution, and compare with the result of multifocusing static solution. So again, we use the parameters estimated at the first step of the multifocusing workflow, the analysis of original press-stack observed data. We can use this information as well in multiple attenuation. The most multiple attenuation procedures are based on the differences between the primaries and multiple characteristics. More differences we can find, more easy we can suppress, subtract multiples. Multifocusing approach allows to do it very efficiently due to the fact that we extract a number of parameters from the original data, and these parameters can be different for primaries and for multiples, even in case when some of them cannot distinguish between these two kinds of events. The other can do it. So first we estimate the parameters, and we define parameters which are responsible for multiples and for primaries. Using parameters responsible for multiples, we compute the accurate multiples model, and then we subtract this multiple wave field from the total wave field using least square solution. Look the example. This is a stack section with a strong multiple at the time about 3.2 seconds. This is the parameters for multifocusing parameters: emergence angle, deep free velocity, and the CMP gather. After multiple attenuation procedure, as I described it before, we built a velocity multiples model and subtracted it from the original data in pre-stack domain, of course. The result is shown here, and you see, if I compare it with the original, that multiples are gone, and we see very clearly the primaries which we couldn't see before multiple attenuation. Now, after this pre-processing, I would say, processing steps, I will show you several applications connected to the imaging part. And the first and the basic application is zero offset imaging, or how we say, just stacking. Again, I repeat that this stacking is based on accurate approximation of the time surfaces, which are arrival time surfaces for reflected and other kinds of waves, which are shown here in green again. So we use the same multifocusing parameters we already estimated at the first step, and we stack this green surface instead of compare it to purple line, which is the CMP trajectory. Like this is another representation of the same picture, but in the observed coordinates of source shots and receivers. And if for a particular CMP position, we stack now all the green traces shown in green crosses. We stack it coherently into the CMP position, instead of stacking only few traces which belong to the CMP geometry configuration. Okay? Of course, stacking more traces lead to increase on signal to noise ratio and stacking power. All these examples which are shown in many our I don't know, brochures you saw. Yeah, you know how to look at this. Just compare conventional processing and multifocusing processing, and we see almost everywhere dramatic improvement, increase in signal-to-noise ratio in 2D case, and here example of 3D case when the number of parameters is more than 3. Yeah. And you see here a time slice shown when the conventional processing gives practically noise. Yeah. This is time slices or depth slices of the conventional and the multifocusing. Another time slice from another oil field. Okay, so but multifocusing can be used not only in data processing and unmigrated stacking procedures, but also in can help in migration procedures. So for time imaging, it's straightforward because the approximation, the multifocusing approximation, this double square root equation, can be modified easily into time migration approximation. It's enough to put the angle, the emergence angle equal to 0, and 2 radius of curvatures RCRE assumed to be equal to RCE. So in fact this represents the diffraction travel time surface, and then the multifocusing approximation becomes accurate approximation for time migration. So using this operator, we apply to the data, and as a result we get the time migrated sections. Yeah. So you see the left hand side, and it's a conventional processing, conventional PSTM, and the right hand side is the multifocusing press-stack time migration. Where do we have advantage here compared to the conventional? There are several things. The first is we use here press-stack enhanced gathers. Yeah. And probably this is the most effect we see here of this pre-processing procedure. Yeah, so the gathers, the input gathers to our procedure, to our press-stack depth time migration, is the enhanced gathers. Second, the approximation, although the multifocusing approximation, although it is very similar to the conventional one, it's have differences because it operates not with the so-called migration velocity, but it operates with the wavefront parameters estimated at the first stage. And the last point is the topography. Our press-stack time migration works directly from topography, and all these 3 factors together provide or give the benefit. Here you can compare the results, and there's several other examples. And always you see the improved image of the multifocusing press-stack time migration. Sometimes it's dramatic, like in this case. Now I come to the depth imaging, more close to the depth imaging. And put your attention that until now we didn't use any depth processing. And so on the stage of parameter extraction, pre-processing, processing, and time imaging. Now after we have all the information obtained from the time imaging, we can start to build the velocity model. So we are here already. Eh? velocity model, which is the crucial step for depth imaging. So there are several things I want to emphasize here. First is we use for velocity model building, we use the enhanced Prestag gathers, not the conventional, not the observed gathers, but enhanced gathers. Of course, it gives more reliable and accurate estimation for the parameters, which can serve as input for velocity model building. The velocity model building itself can be used the same as in conventional, all the types of tomography, tomographic approaches, travel time tomography, stereotomography, and so on. But the input to these procedures are multifocusing parameters. And if the input to these procedures is more accurate, of course, the resulting model is better. I'll show you example of Marmousi type model. This is the true velocity. This is the Dix type of inversion. And this is the multifocusing velocity inversion. This is the estimation using the multifocusing scheme. And as a result, compare it to the true velocity. Yeah. As a first initial macro model approximation, the velocity obtained by multifocusing is not bad at all. Of course, it's better, we can see it on the depth image itself after PSDM, after Prestag depth migration, the true, the Dix type velocity versus multifocusing velocity shows much better results and more close to the true velocity Prestag depth migration. There are several more points about the Prestag depth migration which are under development today in GeoMash. That multifocusing parameters can be used for Prestag data regularization and interpolation. One interesting point is the data decomposition as reflection, refraction, separation, which can be based on multifocusing parameters. Beam migration, which is quite popular in the industry, can be also implemented using multifocusing parameters, and in this way the depth imaging or Prestag depth migration can benefit from the multifocusing strategy. Something like this. So the last point I want to show you is the reservoir characterization, or the use of multifocusing parameters for reservoir characterization, in particular diffraction imaging. So diffraction imaging is becomes more and more popular last few years, and it's based. So the target of the purpose of diffraction imaging is to find, to determine the fractures, the faults, the small-scale objects in the subsurface. And the diffraction is the direct indicator of the small-scale heterogeneities in the subsurface. So today more and more evidences that diffractive component of the wave field can be connected to the high resolution, or sometimes even called super resolution. In multifocusing, diffractions or diffractive component can be easily defined from the same from the general approximation of the multifocusing by assuming the normal incident angle equal to 0 and the equality between the two radius of curvatures. Put attention that this is very similar or almost the same approximation which we use for Prestak time migration. And then assuming these two radius of curvatures to be equal, we shrink in fact the reflection surface to a point. In this figure it's a point N. Yeah? And the two radius of RCRE becomes equal to RCE. It's here just R. And the multifocusing formula becomes very similar to double square root equation of Prestak time migration. This is a synthetic example when we put a fracture zone in one of the layers. Fracture zone was modeled, in this case is two-dimensional cases, which was modeled with 8 fracture corridors with different density of the fractures. Each fracture was modeled by a small inclusion heterogeneity 1 meter by 30 centimeters. As a result of the modeling, we see that additionally to the strong reflection waves, we have a lot of scattered waves, and this scattering is coming from these small-scale heterogeneities. Using multifocusing diffraction approximation and multifocusing diffraction imaging, we separated, in fact, diffraction from reflection coefficient components, and the image of the diffraction imaging shows mostly the diffractive component, all these hyperbolas in the unmigrated domain, and small residual reflected component. After migration, of course, we see diffractions only, so we can see all the fracture corridors. It's 1, 2, 3, 4, 5, 6, 7, 8 fracture corridors, and the faults which are in the model. This now I show you the examples for real data example. One is a simple 2D line from the Mediterranean. This is the conventional stack, yeah? And this is the diffraction imaging, multifocusing diffraction stack. And you see that from the same data, yeah, this was obtained from the same Prestak data. One time we see the reflective component of the wave field. The other time is the diffractive component of the wave field. And after migration, of course, they are migrated on the correct positions, and we can interpret a lot more accurate information about the faults and fracture zones. This is a combined image when the background is the conventional migrated section, and the color shows the diffractivity, the amount of diffraction energy. The more complex example is 3D from the Siberian area of Russia. It's so-called Bazhenov formation. So the conventional image, conventional time migrated image shows in a zoom picture shows the structured situation. We had several wells, production wells, and this reservoir is known as a fracture reservoir. So this is the not interesting, probably time maps, depth maps. What is interesting is that that using the well information, the fracture zones were interpreted and correlated with the energy obtained from multifocusing diffraction imaging. And here in red you see there's the fracture zones interpreted from the log information, from the well information, and this blue seismic trace shows the energy of diffraction imaging. There is a strong correlation. This is not, it is bullshit. This is bullshit. I don't know how it comes to me. This is the combined image when the color shows the result of diffraction imaging, and it is it has a very strong correlation to the structural elements connected to the fracture zones and faults. This is another line extracted from 3D cube, and again increasing evidence of fracturing in areas of uplift and compressions. When we look at the different well positions, we see again this very good correlation between the diffraction energy and fracture zone interpreted from the well information, almost everywhere. This is three different well locations. Finally, we constructed a diffraction image horizon map, and cross plot shows a very good correlation. Here is about 0.7 correlation between the diffraction amplitude and production rate. This shows another cross plot between something which I don't understand very well and the diffraction amplitude, and the average correlation coefficient is 0.88. So this is okay. So this is summary. Okay, Dror, I finished.
המון תודה.
It's difficult.
אני רק שנייה, אני אעצור את הרקורדינג.
כן,